All right. So today's topic is about the applications of SDT. So construction of parse tree is what we are familiar till now. So we need to understand about the syntax tree generation also, right? We don't have much difference between the syntax tree and the parse tree. Syntax tree looks exactly the same way as that of the parse tree, but we don't have non-terminals in the syntax tree. But in parse tree we have non-terminals as well as the terminals. That's a major difference here when it comes to the syntax tree and the parse tree. So first topic is about the construction of syntax tree. SDD are useful for construction of syntax tree. A syntax tree is created in the form of a parse tree which looks in this way. So E is tending to E plus T, E is having T star F or digit it might be, and yeah, it is condensed to the same. So here T is giving me the digit. So if considering this as a parse tree, so the syntax tree for this is where I eliminate all the non-terminals, right? Here which were the non-terminals, E, T were the non-terminals, right? Eliminating this E, which will be the root node actually, that's the question. So root node has to be within the hierarchy of the particular start node here, which comes as plus, right? So towards the left child of the plus here I have E, in other words towards the left side, eliminating this or taking off this non-terminal, I have another non-terminal T, and again for this non-terminal I have star. So star will be the left child of plus. Similarly, star's left child is 3, star right child is 5, and here for the plus, right child of plus is digit which is 4. So ultimately we get the syntax tree which looks in this particular way. So conversion of parse tree to the syntax tree is pretty simple and straightforward. So we have few steps in order to convert how exactly my parse tree will be converted into syntax tree. So syntax tree are useful for representing programming language constructs like the expression and the statement, and they help compiler design by decoupling parsing from translation, right? So we are taking off the translation part. So we don't have the translation, for example, S attributed or the T attributed has been neglected here. So few of the non-terminals is also taken off. So that's about the eliminating or decoupling parsing from the translation. Next is about each node of a syntax tree represent a construct. The children of a node represent the meaningful constructs of a constants of a construct. So let's taking an example here, a syntax tree node representing an expression E1 plus E2 has label plus as well as two children representing sub expression E1 and E2, right? So we are adding E1 and E2. So left child is E1 and the right child is E2, and this ANDing is the operation which we are doing. So the label is plus and two children are E1 and E2, that's what it specifies. So each node is implemented by objects with suitable number of fields. Each field will have an operand field that in the label of node and addition fields as follows. So whenever you want to generate the label, it has some rules to write it. So operand is what we look for an expression. So if a node is a leaf, an additional field holds the lexical value for the leaf. This is created by the function leaf of operator comma the value. This is our first point. The second one is, so if the node is an interior node, that means it is not towards the end, it's not a leaf. There are many fields as node has children in syntax tree. This is created by the definition node operand, comma, and followed by number of interior nodes. So C1 to Ck are my nodes again, interior nodes, right? So here the difference between the leaf and the interior node is, so leaf will have value at the end because that's the final value, and for the node it is not a leaf, that means it is not in the final end, so it's a node, or it can be any particular node side by side. So example goes in this way. The S attributed definition in the figure below constructs syntax tree for a simple expression grammar involving only binary operators plus and minus. So we have a small example here for a minus 4 plus c construct the S attributed definition is what the question is, right? So we have with how many operators? Two operators. One is minus and the other one is plus. So here concentrating on minus and plus here, I have a production e tending to e plus t. So differentiating this e by, both e are the same but differentiating by this e is differentiated as 1. So e dot new node, this is the one, e dot new node is equal to new node of operator which is plus, right? So new node of operator which is plus. Towards the left hand child I have e1 dot node because it's a node, so e1 dot node, this is the left child, and t is the right child of plus, so this is t dot node is the right child. Similarly, I also have a production e tending to e1 minus t where e dot node is equals to new node of minus, comma, left node is e1 dot node and the right node is t dot node. So e dot t is equals to, as usual, e dot node equal to t dot node. Next one is t dot node is equals to, within brackets, e dot node. T dot node is equals to, here it is a leaf, right? So id is a leaf, that means it's a terminal. None other things are terminal. I cannot have plus as a terminal, remember that, it's a node again, right? So which are the terminals here? id and num are the terminals. So according to the syntax here, what we have with respect to leaf is, so leaf is equals to particular id, or it was terminal, comma, what is its value, right? So that was the case which we saw here. So leaf of operator, comma, value. So here the operator was one second. Yeah, so here the operator is id and its value is id dot entry because I need to give the value for id. Similarly, t tends to num is t dot node is equals to new leaf of num is the id, comma, num dot value and its own value. This is about the semantic rules which will be given for the syntax, right? And how do we generate the syntax tree? Before generating the syntax tree, we go generating for the parse tree here. So parse tree looks in this way, right? So looking into the case here, what do I have? A minus 4 plus 5. So where do I start? I start with the starting symbol which is e, right? So which is e. So e is giving me e1 plus t. So e is giving me e1 plus t. Then plus is solved. So the right hand side is c. So I need an identifier c here. So is my t term yielding me any identifier? Yes, I have a production t tends to id. So t is tending to id. So similarly, this right hand side, that is plus and c, has been taken care of. So e1 is a minus 4, right? So e is, I have to look for an operator which is minus. So e1 is minus. Do we have a production leading to minus? So yes. So e is tending to e1 minus t. So e is giving me again e minus t. So E minus T. So A is an identifier again. So E2 identifier, what is the, if I have, what is the production? E tends to T, T tends to ID. So E tends to T and T is tending to ID. Similarly, this T is giving me a value, right? So it's a 4. So T should be num. Instead of ID, it should be num. Getting? So this is the parse tree. How do we generate the syntax tree now? So this is the parse tree, and syntax tree is where it will not be having the cases of the particular non-terminals. Exactly, right? So here E is taken off. In place of E, I have E1 plus T. So E1 plus T, what is the semantic rule? Semantic rule is new node, I have to give the plus. I have to create a node which is plus. And left side of plus is E1 dot node, right? Okay, so what does E1 dot node has? E1 dot node has minus. So left child again for plus. 1 second. So left child of plus is E1 dot node. So E1 dot node has left child of minus. So again minus I give. So I come back to this particular node. Right hand side I have what? T dot node. So T dot node. Where do I have T dot node? Okay, T dot node is giving me E dot node again, right? So E dot node is basically T dot node, sorry. So T dot node, T is giving me ID. So T is giving me ID. So what is an ID here? ID itself is a value, right? So on the right hand side of plus, I have ID. So towards the left hand side of plus, what did I have? That is left child of plus E1 dot node. In E1 dot node, I have the ID as minus, right? So I have an operator of minus. So minus, and left child of this is E dot node. So this E dot node has another identifier which is ID. So here this ID is basically C, and this ID towards the left of minus is again itself an ID, and this ID is what? This ID is A. This ID is A. So the right child of this particular minus here is T dot node. So right child of minus is T dot node. So T dot node is having a number. So it is again a number. And what exactly is the number? Looking into the input here, the value is 4. So this is the syntax tree. So this is the syntax tree. Looking into the cases below, as you can see, this is what exactly the diagram speaks. So I have E, E plus T, E minus T, E to T, T to ID, and T to num, and T to ID. Similarly with the syntax tree. The final step is I need to generate the SGD for it. So this is the SGD for the case. Let me change the color. Yeah, so here where did I start in the beginning? So this particular SDD is having both. One is with the parse tree and linked with the syntax tree, right? Whenever you're writing SDD, it's a bit complicated when drawing, right? So first you draw the parse tree, right? So first you draw the parse tree. So I have drawn the parse tree. Here, whatever I draw with the red color will be in the parse tree here. So E dot node is giving me the cases of again E plus T. So E dot node plus T dot node. Fine. The next case is this E is giving me E minus T. Of course, E is giving me E minus T, and E is giving me again T, and T is becoming ID. On the other hand, E1 is giving me T, and T is given as num. Similarly, all the node values I have represented as T. Alright, so the remaining left out part is the syntax part actually. Right, so replacing that with the color here. So E dot node is first operator with respect to plus. So plus left child is E dot node. E dot node is represented with minus. Similarly, left child of id is, sorry, minus is id, right child of minus is my num. So right child of this plus is again id. So this is the parse tree. This is a parse tree. So I am just drawing with the numbers in color here, so representing or that it is a parse tree. Okay, so this is another one, this is the other one. So whatever I have drawn now is the parse tree. Using this parse tree, now we go write the syntax tree. Syntax tree is very simple. E dot node has the value with respect to the case where if we go back there, we saw that E dot node was giving me a new node where operator was plus and left node was E dot node and T dot node, right child was T dot node. So here this was the operator, consider that operator, right, take plus as an operator, right, taking this plus as an operator, the left child of this particular node is what? Minus. So left child is pointing to minus. Similarly, right child is pointing to id. Right child is pointing to id. Right. So again, left child here minus. Minus is left child is id again. So this is pointing to id node. This is a new node. Right. As we know that we have a sort of thing looking like a linked list, right? So linked list has a first node, a left child and the right child, right? So these are the addresses. Basically, if you construct the syntax tree and a parse tree, you can easily construct using linked list, right? So that's the best data structure to construct the ways of parse tree or the syntax tree. Coming back, so here, what does this T node says here? So T node is actually the right node of minus. So pointing towards this box of num and its value is 4. This is a value, num value, right? So this is just an ID, and entry was which was given as A, right? A minus 4 plus C. That was the input which was given. So here it's ID, and ID was having the value with entry, and that was C, right? So this is my SDD, right? So this is the SDD for the example, and this is the parse tree, and this is the syntax tree. So this is what the next particular phase is when it comes to the applications, right? I hope I have made the concept clear here. And do we have any doubts? Kindly let me know in the chat so that we'll get the clear cut information. All right. So moving on, fundamental things. So I had few nodes or few of the particular ports, right? So here, if the rules are evaluated during a post order, right, during the post order traversal of a parse tree, or with the reduction during a bottom up parser, then the sequence of steps shown below ends with P5 pointing to the root of the constructed syntax tree, right? So I'll just write down how it was looking in the previous entry there. So plus the left child was given to minus, and minus was having left child with respect to ID, right? So it was ID, and the right child was given to num. This was num. So again, here I had some value which was 4, and here with the identifier I had A, and the right child of my plus here was towards the phase of another ID. So ID with the ID value of C, right? So here I have how many nodes? 1, 2, 3, 4, 5 nodes. So these are about the entry values, right? So how many leaf nodes, right? Leaf nodes, I have 3 leaf nodes, right? So which were the particular leaf nodes here? This is a leaf node, this is a leaf node, and this is a leaf node, and the remaining terms were of the remaining terms. For example, this one and this one, they are not leaf nodes, they are inner nodes. Inner nodes in the sense they are new nodes, right? So the entry of P3 and P5, right? So this was the first one, this was the first node or the port, and this was the second one, right? And this 1 and 2 gave me the value of 3 here. So fourth one was my new identifier. 3 and 4 gave me with the value of the fifth one, right? So ultimately P5 is new node plus, and towards the left child of plus here is who? The third node, so P3, right? So the P3 here, and right node of the right child of P5 is P4. So you can see here P4, right? So similarly, left child of new node of minus is P1 and right child is P2. All right, so P1 and P2. So that's about the steps in construction of syntax tree for A-4 using some ports here. If you have any doubts, kindly let me know. Next case is about constructing the STD for top-down parsing. Fine. So here, with the grammar designed for top-down parsing, the syntax tree are constructed using the same sequence of steps which were used before with the S attributed and the L attribute, the same way, and we are trying it out, right? So the structure of parse tree differs significantly from the syntax tree. The L attributed means what? I have both synthesized as well as inherited attribute information performing the same translation of S attributes shown before, right? So this is an example here. I have production. Let's understand what exactly are the particular attributes which I have written here, right? The first case is E is tending to TE dash, right? So as I said, this value will be sent to here, and this value is sent to here, right? So this E dash dot inherited is getting the value from T dot val or T dot node. That's about this statement. The next thing is this value is getting the value from E dash. So E dot node is getting the value from E dash dot synthesize. E dash dot synthesize. That's about this. The second term is E dash is tending to plus T E1 dash, right? E dash tending to plus T E1 dash. Here we got a particular node that is plus. So what do you understand from here? So here the left child of my plus is E dash and right child of plus is T, right? And basically plus left node, right node is assigned value to this particular node. So the E1 dash dot inherited is getting the value from all these three things. So one is basically E1 dash dot inherited is equal to E dash dot node plus T dot node, right? So new node is equals to, what is the new node? Which is plus. So I write plus here, and which is the left child? Who is the left child of this plus? E dash, and it is inherited. So E dash is getting the value and inherited, and towards the right side I have T. So T is a node again, right? So this is T. Next case is here I got to know about the value of E1 dot inherited, but I need the value of E1 dot synthesize. So how is it getting? E1 dot synthesize is getting the value of E1 dash dot synthesize. When we draw the next particular case, whenever we draw the dependency graph, you will easily understand about this case if we take an example. The next case is E dash is tending to minus TE dash. Same way, same application. So this particular term here will be assigned the value to here, from here to again synthesized, right? So E1 dash dot inherited will be equal to new node of minus, left child is E dash dot inherited, right child is T dot node, exactly the same. And as I have E1 dash dot inherited, I have to give it to synthesized, of whom E dash. So E dash dot synthesized equal to E1 dash dot synthesized. Next case, E dash tending to epsilon. As I said, E dash, if any production tending to epsilon, straight away E dash dot synthesized is equal to E dash dot inherited. Next is T dot node is equals to E dot node, no left, no right. Next, T dot ID, so here it is an ID, right? So ID comma ID entry is what the value which I am assigning to T dot node. Similarly, T dot node here is equals to new leaf of num comma its value, right? Num is a value, ID is an entry. Solved about this. So looking into these cases here, we should be able to write down the dependency graph now. So looking into the dependency graph, okay, it looks a bit clumsy here, no issue, but yeah. So which was my first production? First production was E tending to TE dash. So E is tending to TE dash. Let me write down my parse tree for A minus 4 plus C so that it will be easy for you to construct. So I have E, so E is giving me TE dash. So I have T and here I have E dash. So T again, it's an entry which is an ID, right? So followed by E dash here. E dash is A has been tackled. So here ID will be my A, right? So on the other side I have minus. So do I have production where E dash is giving me minus? Yes, E dash is minus T E dash. So minus T E dash. So similarly this, okay, minus T E dash. So T is giving me num anyhow, right? So the num value or num value has been recovered. The next comes E dash here. So I have E dash. So minus has been tackled, 4 has been tackled. Next I have to deal with plus and another entry, right? So E, does it deal with plus? Yes, E dash is having an equation of plus T E dash. So plus T and E dash. Anyhow, this E is epsilon, and here T is giving me my identifier, which is the identifier, C is the identifier. Okay. Yes. So the next thing is this is my parse tree. Next case is I have to draw the SDD with L attributed is my requirement, right? So first is I give the value of num and ID, right? So here my num value is 4 and this is A and this is C. So first step is assign the value. So that will be my first step. So the next step is once you have the value, push it towards its upper nodes, right? So from A, T value, that is T dot node value, it's getting the value of A again. All right. So from here to here is what I need to send. So from first stage to this is my second stage. Similarly, from my third stage, which is 4 value, I am pushing it to T. So this is my fourth stage. The other thing is T and T value should be sent to E here, right? So this is my fifth one. So once I have 5 here, this E value will be pushed again towards this E dash. Okay, so that's my sixth step. So this is sixth step, and from this value with minus I have to get the value, right? So from here I get the value, both value I get it. Basically it is A minus 4 is already, I have the value here in the inherited value. Okay, that is E dash dot inherited value, I already have the value. Next, from here again the value goes towards this E dash of inherited, right? So this is 6, And the other thing is, okay, this 7 to 8 is what needs to happen, because this is again entry. So this is 7, I get the value from here, this is 8, right? Plus and 8 both will be given to the value here. So this will be my value 9, right? From 9 I generate the value to itself. That's about the synthesized, right? So that is 10, right? From 10 here, from this synthesized to again e dash dot synthesized, this will be my 11. So this is my 11. From again e dash dot synthesized will be pushed towards its value of e dash dot synthesize here, right? So this will be my 12. So from the 12th step I give it to e dot node, right? E dot node, and this is my value 13. So this will be my 13th step. So that's about the SDD here for the case, and if you have any doubts, kindly let me know. And this is about one important topic, applications of syntax tree and SDD when it comes to the syntax tree. All right. Next case is about the structure of type. I'll just give you a gist here what exactly it is. So it's an example of how inherited attribute can be used to carry information from one part of the parse tree to another in C. The type, okay, this is basically one example. Int of, it's an array of 2 and array of 3. It is read as actually array of 2 of array of 3 integers. That's how we read this statement. So this is array of 2 of 3 of integers, array of 2, array of 3 of integers. So here if I look into the case, this will be my the value or the input string, that is array 2 comma array 3 comma integer. This will be my input, right? So let's understand how we got the input. So looking into this, which is my first ID here. So first array is this, right? This array's left child is 2, right child is complete these 3 things. So in this right child is, left child is 3 and the right child is integer, right? So let me explain you again. So this will be my root node, that is array. Array's left child is 2, right child is the complete thing here, right? So for the node here, that is again an array. So this array's left child is 3 and this array's complete right child is integer. That's what I have written. So node array, left child is 2 and right child is complete this thing. So right child is array. Array's left child is 3 and right child is integer. The next case is the production. T is tending to B, C, and semantic rule is T dot small t is equals to C dot T, right? How we got this? Anyhow, looking into the case here, this C is getting the value from B and T is getting value from C, right? So that's why T dot value is equated to C and C dot value is getting the value from B. Next production is B tend to integer. Integer is a terminal. So B dot value, B dot T attribute is equals to integer. Similarly, B dot T here is equals to float. So this is C dot T is equals to, what do you have here? This is array of num. So array of num dot value, and this is left child, right child is again C node itself. So ultimately C dot B is equals to the C1 dot B, that is C1 dot B is getting the value from C dot B. So looking into another production where I have C tending to epsilon, as I said, C dot synthesized, or the T attribute here is equals to C dot B, right? So generating the graph here. Anyhow, if you look into the above example, the non-terminals B and T have a synthesized attribute T. So here T refers to synthesized. Remember, T is synthesized, B is inherited. That's what it says. So the non-terminal C has two attributes, an inherited attribute which is B and a synthesized attribute T, right? So inherited attribute B, pass a basic type down the tree, the synthesized attribute T accumulates the result, right? So here B is inherited, from B I get the push the value towards the synthesized attribute which is T, and unrelated parse tree for the input is int of array of 2, right? Array of 2 integers, that's what it says, array of 2 integers. So in order to get into the case here, let's work out with the case. So I have T, because T is my starting state. So T is giving me BT, right? One is with B and the other one, sorry, BC it is. So B and C, and looking into the case of production, B was giving me value of integer here, right? So B was giving me with the value of integer. So B is int, and C was giving me with the array. So C was giving me with open brackets, num, close brackets, right? And also C. So it was open brackets, num, and close brackets, and again it was a C, and anyhow C had a production which is epsilon, right? So this about the parse tree which you can see. So how the values goes, right? So this is B dot T, that is B dot synthesize, because the value of int should go up. So if I am getting the value from child to parent, then it is synthesized. So B dot T is equals to integer, and so what about this value here? This T is getting value from integer again, right? So basically C dot T dot B is equals to, I am getting the value from here, which is the value I am getting here, integer. So it is integer, and C dot T can get the value from its sibling as well as from itself, right? So here is where it is getting the value of number, right? So this value 2 will be here. So basically it is array of whatever is the value which 2 comma integer. So num value is 2, and what is its left child value which I got? It is integer, right? So 2 comma integer, and ultimately the C is where the next value will go to C with respect to integer, and again it comes back here, right? And again it goes to here. So if I number the particular value here, so this is how the numbering goes. So this is where I start. This is my step number 1 from, okay, he has omitted this step here. So okay, let us consider this step as 0. Fine. So 0 to 1, right? So 1 to, I have to give the value to C dot B, right? C dot B. So this is 3. So before going there, I need to generate value here. So this is 3. This will be my 4, right? From 4 I am pushing here, this is 5, and 5 to itself it is 6, and 6 towards its top it is 7, and basically from here to its parent node this is 8. So this is will be the topological order of the particular value for my SD or the dependency graph here, right? So this will be your assignment. Solve for the same production, and